policy iteration for time step. So it's all time step based analysis. So this is not really for this policy, but we have a time step t is t minus 1 into okay. So for any policy.
Oh, so you mean to say that we are going to do the same value iteration, but now we don't have to choose the actions, we would rather use the actions of the policy value.
Yeah.
Okay,
That's
that makes sense.
So initially we have 0 and you can basically iterate through this. You see for each action you compute this v value, and so for each action what we do is now basically compare these two, which is s by s into or just reward based. We have if there exists any action, so if this value is greater than or equal to greater than this value, then we basically update our pi with a. So we will say that pi s is now a. Okay. So once we choose a random policy, we go through state by state and say that if and for each action we'll evaluate which is the best action, we'll see based on the v values, and if that value is greater than your existing policy action value, then you update your policy.
Okay.
So basically, we have to solve this equation basically for Vs. So the way it works is that we have to find a Vs such that this equal to this happens. So that's how we determine this Vs dash to begin with. And the way to do it is exactly once again, taking it as t and t minus 1. You get it? So we choose a random policy, and we want to get the value function for that policy. And value function for that policy would be this exactly. Right? But how do we get it? It's a recursive definition. So for that, we do basically multiple iterations. There are also other methods in maths, but this iterative version works. Again, you start with some 0, you keep updating until it saturates. So that's the value. Once you get VS, you do all this checking and see if something changes. If something changes, once again you have to compute VS. Again, so many iterations.
I see. So one definition. So Dr. Rao had said in the class that value iteration would be searching in the infinite space of all values that you can have,
Yeah.
whereas policy would be searching in the space of a
Yeah.
finite number of things, that the number of policy. But here, if for every policy we are still doing the value
No,
iteration.
no. So here there is no max. You just have to converge. That's all. So it's a simpler problem than having max in the equation.
But we are still trying to find the max to replace the action in the
Yeah. So the number of replacements are finite here. So that's the advantage.
Okay.
So just have to do this. So solving this is the only difficult part. Once we solve this, these are finite number of steps. How many changes can you make? So for each state, there are only, mod a number of options.
Okay.
Right? So this is a finite space, which is, a power s. Okay. So the only tricky part is, to do it on the board, you have to do it for multiple times in the Vasavis. But when you actually, code it off, this may actually take less time than this. Do you want to do it?
No, not me.
So have you guys coded this value iteration or policy iteration? You said that MDP assignment is over.
Yes, but so that is a different. So the assignments don't have any of this as a coding.
Oh, no coding was there? Or
Regarding MDPs, no.
oh,
There was a homework, but not this one.
oh. Do you have any projects on MDP?
We don't know.
Any questions? Example of this one? So, yeah, that's what I think. So, you choose this policy, initially a random policy. Once you choose this, you have to solve this. Okay? You have to obtain a VS which satisfies this. Okay? How do we obtain a VS which satisfies this? So, initially assume that all VS's are 0. And keep updating. So if always a 0, then solving is done by doing this repeatedly. When this converges, that means that whatever the value VS is, that is satisfying this. So now we are trying to find VS which satisfies this by doing this repeatedly here. Initially we assume 0, then you keep iterating. What happens when you draw? It will be 0, and here it will be 0. Is it 0 or that actually 2?
Won't be.
So, yeah, we have to
Yeah, this
consider
one.
all states, I think, right?
Yeah.
We have to put all states.
Maybe you can use the same table.
Yeah.
Yeah.
So, yeah, initially we have 0. Then here for draw action we have to see all these will be 0. Here we can't perform any actions. So these will just get updated to 2, 3, 4, 5. Fine, right? That's how we update it. VDS is RS plus something. So these will be 2, 3, 4, 5. Then here for draw action, what will happen? This will stay 0 because all these are 0. These will get updated because this won't get updated. If you draw, this will become how much?
0 only because
0 only.
yeah.
And if you draw 0, all draws will lead to zeros, but RS is 0, but DS is, and VS prime is basically related to these. Okay, so all these will still remain 0, and this will remain 2, 3, 4, 5. Okay, fine. So we converged. So this is the initial value. That's it, because nothing changes. So initial values are for this function, these are just, because you are drawing, you are not considering the stop action. So your values will be 0. Okay, for other states, you can write it down. So this is the one for pyrene. Okay, once you have this, now you go and check for each action what happens. So we have already seen it is converging so fast, right? This one, the other one, because of considering both actions, we are not converging fast. Here we converge fast. But what happens? These combinations we can't get by, right? We have to consider it someplace. We consider it when we are considering it for each state. Is there any alternate action which does better? That's when we end up doing these calculations, right? So based on this, so if you see, what if you do stop? What is your new function? If you do stop, you will go here, which is R value is, R value of this is 0, and the transition function is also 0. V value of this is 0, right? So nothing gets changed because you haven't found any better action. So this will continue to be draw. Here what will happen? What happens when you do stop?
You get 2.
We get 2. So that's interesting. Will we get 2 or? Yeah, we get 2. Stop will go directly here with 1 probability. So we get 2, which is better than 0. And if we do draw, we'll get 0 because of this row. So now we are saying that here it's better to stop. Okay? And what happens here? If we do stop, stop is better. Stop is better. Stop is better. Right? Because all these guys will lead to these steps. So this is our new policy. Now for this policy, once again we have to solve this linear equation, which is Vs. For that we have to start with this and apply those actions, and we will get a new set of stuff. Okay?
So how would you determine which policy is optimal now? I mean,
so when we converge, when we finally converge, when there is no action which is better. Suppose here we see that these actions have changed. So at some point we'll see that none of the actions are changing, so the policy is not changing. So that's when you are converging, and that is optimal.
Okay.
So naturally we expect that at some point this will change to draw, right? Maybe in the next step itself.
Okay.
So how do we know that it converged?
I mean, yeah, the conversion is optimal.
Yes, I mean
The
because
proof that value iteration actually stops with the
No.
optimal policy.
the policy iteration converges.
Yeah. Policy iteration converges with optimal policy.
Yeah, I mean it could be a local optima. We have, I mean, it could be the case.
Yeah, so it feels like there could be a local optima, but basically in this case, in MDPs, local optima is global optima because your actions and utilities, basically your effect of actions is restricted to the current state only. So it
Okay.
doesn't matter what all is, how you reach that state. Markov process by definition, restricts the effect of actions to only the current state.
Okay.
So that is basically a guiding point to the proof. Full proof, you can see online or anywhere. But that's basically because of that. Because the effect is only based on current states.
Mm-hmm.
So as long as you are checking locally that nothing is changing. If nothing is changing around your neighbors and their neighbors and their neighbors, it's fine. You can say that this is optimal. If somewhere something is changed, that may cause a ripple effect. We keep on going, right?
Mm-hmm.
If nowhere nothing is changed because you are only affected or as good as your neighbors haven't changed, their neighbors haven't changed, nothing has changed. So this local optima is actually the global optima.
Mm-hmm.
So shall we do this actually? Just one more step, I think we'll find drop.
Mm-hmm.
If you want to do this, the way to do it is this. So maybe I can just erase this. Okay? Yeah, sure. You can come.